Okay guys, now I want to take a look at the next section in chapter R. We're looking at chapter R.2 today, which starts at, we're going to do a little bit more than that, but we're going to start with R.2, which starts on page 18, if you guys are following along in your book. We're going to look a little bit more at our exponents today. So we talked real briefly last week about what exponents are and what they represent. And today we're going to look at some different properties with our exponents and some rules that we can look at with those. So in chapter R.2, on page 18, we're looking at, it says simplifying expressions with zero and negative exponents. So here's our rule for those. And actually it's probably better explained over on page 19 when it's showing us that chart that shows the definition of anything that's raised to the power of zero or anything that's raised to a negative exponent. And this is just something that you just need to really just kind of remember. Because I wish I could explain it a little bit more, but anything raised to the power of zero, doesn't matter what that is. So say 4 to the power of 0 is always equal to 1. Doesn't matter. Even if they use in the explanation on that chart on page 19, they use the letter b just to show that as that variable can represent any number whatsoever. But b raised to the power of 0, always equal to 1, no matter what. No matter what. The thing to look out for, so they even use the example, they show 5,000 raised to the power of 0. The answer to that would be 1. They even show negative 3x in parentheses here, raised to the power of 0. And this is something that might come up on your homework. The parentheses here hold that number in place, and they're raising that entire thing to the power of 0. So that's why that entire thing is 1. If for any reason, if those parentheses weren't there, if this was, say, negative 3x to the power of 0, be careful with that. Exponents are always attached to the number it's directly next to. So this exponent, this 0 here, is actually only associated with this x, not the 3x. So really, that's the only part that would be represented by 1. Because again, anything raised to 0 power is 1. So technically, this number right here is the same thing as negative 3 times 1, which we know is negative 3. So anything raised to the power of 0 is always going to be equal to 1. So keep that in mind. So yes, so just looking at another example, if I said, let's say 4x to the power of 0, that 0 is only on that x, so therefore this would be 4 times 1, which we know is going to be 4. Only that anything to the power of 0 is always 1, but it's only this part that is, raised to the power of 0, so that's the only part that's represented by 1. So that says right now, it says 4 times x to the 0 power is another way that you could break that down. You could look at that as 4 times x to the 0 power, and therefore that's why only that part is represented by 1, if you want to look at it a different way. But again, throwing those parentheses around the entire thing. So if I said 4x, but put that entire 4x in parentheses, now that entire thing is being raised to the power of 0. So therefore that whole thing now is represented by 1. So if you're seeing those parentheses, again, keep that in mind, that anytime you have an exponent, it's only attached to the number that it's right next to, or variable in this case. So that's why you're seeing that. Anything in front is not associated with that. So something to think about. So anything to the power, we'll look at some more examples, but anything to the power of 0 is 1. And like I said, we'll look at some different examples. The second thing in there shows that anytime we have a negative exponent, you never want a negative exponent. So this is a rule that I really kind of have a hard time really explaining. They show it this way on the chart. They show that anytime I have any number raised to the power of a number that is negative, so they show that as negative n. What I'm going to do is I'm going to flip that. I'm going to use what's called the reciprocal, which is, if anybody's familiar with the reciprocal, it's a flipped version of that fraction. So where b is the same thing as b over 1, if anybody's familiar with fractions. To better explain that, if I gave you guys, any number, that 3 is the same thing as 3 over 1. So the reciprocal of that would be flipping these two numbers, would be calling that 1 over 3. So that's how we, when I want to get rid of a negative exponent, we use the flipped version of that number, what again we'll call the reciprocal, and we'll use that positive version of that exponent there in the denominator, which is the bottom number. So b to the negative nth power is going to be rewritten as 1 over b, but to the positive n. And so they show that as they flipped that. In fact, they show kind of this intermediate step here. They show that we flip the b over 1 and make that 1 over b, and we instead raise that to the positive version of that number, and that becomes then 1 over b to the nth power. So you really don't even have to think about this step at all. Just remember that anytime you have a negative exponent, we are going to want to see that as a positive exponent in our bottom, in our denominator. And I'm going to show you some different examples with that and where we might see that, but they do give a couple examples there in your book. They show that if I have 4 to the power of, say, negative 1, we're going to flip that and just make that 1 over 4 to the power of 1, but 4 to the power of 1 is the same thing as 4, so that could just be reduced to 1 over 4. Anything that's raised to the power of 1, that's just like saying 4 multiplied one time would just be 4, so that's why this would reduce that way. They have another example, and they show that if I have, and they're showing with a variable, that if I have x to the power of negative 3, that's the exact same thing as just 1 over x to the third. Keep in mind, again, that exponents are only attached to the variable or the letter they are directly next to. So if I gave you guys something like this, if I said 7x to the power of negative 2, remember that that negative 2 is only on this x. So really 7 can stay where it is. So 7 is going to, so when we simplify this, 7 is going to remain on our top, so on our numerator, if you if you are familiar with fractions, but it's only this that we're going to move to the bottom. So this will become x to the power of to the power of positive 2. So keep that in mind. Whereas then again, if I put parentheses around that whole thing, if I said 7x to the power of negative 2, now that negative 2 is on this entire thing. So this would be rewritten as just 1 because we need something in the numerator. Anytime we don't have anything there, we just use 1. So 1 over 7x to the positive 2 is how we would write that. So just kind of a heads up on that. And we'll see some more examples with that, but I want to show you guys again that rule states that anytime we have a negative exponent, make sure that that just gets moved to a denominator because we're using the reciprocal. Some different rules that I want to go through. I'm going to put them all together here in just a minute. Some of them we'll be able to see together, but I want you guys to turn over to page 20 and 21 and actually look at the top of page 21, and we're going to look at some different properties of exponents as well. So some different properties that you guys would see there. I'm starting with the very first one. This is our multiplication property. It's sometimes referred to as the product rule, but this says this, that if I have any number, so let's say we use b as they're showing on the chart there. If I have some number raised to a particular power, if I multiply that same exact number that's raised to a different power, an easier way to solve that would be to simply just write that number, and then we are simply just going to add together those two exponents. So they use an example here. They use variables. They use the variable x, and they say that if I raised x to the power of 4 and was multiplying that by x to the power of 3, then that can just be simplified as x to the power of 7 because I've simply just added together my two exponents. And the way that that works, if you look at that expanded form, let's think about what x to the 4th means. X to the 4th means x multiplied 4 times, right? And then x to the 3rd means x multiplied 3 times. So if I'm multiplying that, then I just have another multiplication number in there, and there you can see now I have x multiplied 7 times, which I can write as just x to the 7th. So it's just a simpler way of showing that when I have this, as long as it's the same number. The same thing works with when you have actual numbers. If I had 5 to the power of 2 and I was multiplying that by 5 to the power of 4. This would be simplified as just 5 to the power of 6. Now, yes, I know I can simplify that a little bit further and actually take 5 times 5 times 5 times 5 times 5 times 5, so 6 times. But on next week's quiz, I'm only going to have you guys simplify it. I'm looking at next week's quiz right now, and in the directions it does say to simplify each expression. I can't talk today. It says to simplify each expression, and it says you do not have to completely solve. So you can leave it at this, and that would be totally fine. Now again, if you did completely solve that, and you took 5 times 5 times 5 times 5, I've lost track of 5s. Hold on. I'm going to use my better calculator while I'm quickly talking about this. 5 raised to the power of 6 would be 15,625. If you actually solved that, I mean, I'd still take that. But again, let's make it short and sweet, and let's only just have to simplify it. So that's why. I do want to understand those. I want you guys to understand that multiplication rule and all these different exponent rules, because they will come up when we look a little bit deeper into linear equations next week. So keep that in mind. Again, and that worked because, remember, 5 squared is the same thing as 5 times 5, and we are multiplying that by 5 raised to the 4th, which is the same thing as 5 times 5 times 5 times 5. So since we're multiplying those two, so that means there we just see 5 multiplied 6 times, and that's why that worked. So this only works if you have the same base. If you had 5 to the power of 2 and you were multiplying it by 6 to the power of 4, that will not work. That product rule does not work here. You'd actually have to solve that out. And, actually look at, 5 squared, which is 25, and 6 to the power of 4, and go from there and actually multiply that. But to save yourself the trouble, when you are looking at two numbers that happen to be the same number, and you're raising them to different powers, that can just be simplified that way. And again, this will come up as we go through the next couple classes. So that was what's called the product rule. When we're multiplying two numbers, we can simply just add together the exponents. So opposite effect takes place when we're dividing our two numbers. If we have some number raised to any particular power, and we're dividing that exact same number by that's raised to a different power, we can simplify that by looking at that as the same number, but just those exponents being subtracted. So if I had 4 to the power of 7, and I was dividing 4 to the power of 3, that could be simplified as 4 to the power of 4, because again, I'm subtracting those two exponents, the 7 and the 3. They use an example. Let's see, what are they using? Okay, they have, and I will show you how this works. So if I have, say, t to the, oh, that's a highlighter. Didn't mean to do that. Okay, t to the power of 6, and they're dividing it by t to the power of 2. That would be t to the power of 4. And a way that you can think about this, because t to the power of 6 is t multiplied 6 times. So there's 6 t's up there. And then they're dividing it by t to the power of 2, which is t multiplied twice. And when the same number is on the top and the bottom, they pretty much just cancel each other out, which is what happens here, and that's why you can see I'm left with then 4 t's up at the top, so that could be represented much easier as just t to the power of 4. And that's how that would work there. So that's just a simpler way of looking at that. And then don't forget your negative exponent rule. If you ever subtract two numbers and you end up with a negative value, you have to take it a step further. What I mean by that is, let's say we have this. Let's say I have x to the power of, say, let's just look at 5, and I'm dividing that by x to the power of 7. Then remember, if I take, so I know it's going to be x, but if I take 5 minus 7, we know that that's negative 2. So that would be simplified a little bit further as x to the power of negative 2, which again, when I have a negative exponent, I don't want that to happen. So that would actually be taken one step further, and we would actually simplify that as 1 over x squared. But let's look at that and break that down, and I want to show you another reason as to why we can do that and get to this answer, that 1 over x squared. Looking again at this problem here, so let me get this out of the way. So here's the original problem. Thinking about how we can factor that out again as we've at the expanded version of this. So x to the 5th, and I'm just going to try to quickly write this out, will be x multiplied 5 times. Dividing that by x to the 7th, there's x multiplied 5, now 6 and 7. You guys see where I'm probably going with this. Remember, when you have the same numbers on the top and the bottom, they will cancel each other out. So those first 5 x's will all cancel each other out. And you can see what ends up happening here. I end up with nothing on top, but I do have 2 x's down there in the denominator. So instead, it's just easier to look at that as 1 at the top, again, because 1, there's nothing up there, we can represent that with 1. 0 would not work. It's just be 1. Because 1 times anything we know is anything, and so those 5 x's, x to the 5th is the same thing as 1x to the 5th. So there's always an assumed 1 everywhere. So we look at that as 1 over x squared, because that's represented with those 2 x's right there. So that's how that works, and that's why we would take that a step further, because we never want to have a negative exponent. So something to keep in mind as you're going through that quotient rule. The quotient rule is what we just looked at, that when you're dividing the same base of 2 different exponents, you would just subtract, but sometimes when you subtract, you end up with the possibility that you might have a negative exponent, so keep that in mind. You want to take that a step further. Okay, the next rule is called our power rule, and our power rule says that anytime we have any number, so any number, we'll just call it b again, raised to a power, but then we're taking that and raising that again to another power. A quick way of solving that would be, our answer would just be that same number, but we've just multiplied those two, we've just multiplied those 2 exponents. So b raised to the power of m, then raised again to the power of n, would just be the same thing as b raised to the power of whatever m times n is. So looking at an example, if I have, say, 4 to the power of 3, and I raise that again to the power of 2, that would just be 4 to the power of 6. And again, let's think about what that represents. Let me get all this out of the way here. So we just had used 4 to the power of 3, and I was raising that again to the power of 2. We can call this 4 to the 6th because remember what's happening right here. 4 to the power of 3 is 4 multiplied 3 times, and it's telling me to take this and multiply it, according to my exponent up here, I'll cover this in blue so you can see it, is saying to multiply this whole thing twice. Well, then we'll do it again. We multiply 4 to the power of 3 twice. So therefore you can see we have 4 times 4 times 4 times 4 times 4 times 4. So in other words, we have 4 to the 6th. So it's just much easier, obviously, to just look at it that way. So our power rule says that if we have any number, so there's x, and let's say we raise it to the power of 4. So any number raised to any power, but then raised again to another power. So x to the power of 4 raised again to the power of 5 would simply be x to the 20th. We just multiply those 2 numbers together. Okay, the next couple rules, a way to kind of think about all of these really would be to kind of think about the distributive property. When you're dealing with parentheses, anything outside the parentheses can be easily simplified by distributing that. So in the next one, it says if I have 2 different numbers, but they're raised to a particular power, well, that's the same thing as if we could take the first number raised to that power, multiply it by the second number by that power. So they use the example, if I have 4, I'm not writing anything. If I have 4x and that entire thing is in parentheses, and raise that to the third, well, that's the same thing as 4 to the third, and we're multiplying then that by x to the third. And then 4 to the third, we can actually simplify that a little bit further. 4 to the third would be 4 times 4 times 4, which is 64. So this is the same thing as 64x cubed. You know, so you could even take it a step further. I know they didn't do that in the book, but that's just a way to think about that. And they show that in that expanded form. So that's something that may come up as we start putting these together, just a different way of thinking about that. And the same thing goes when we're dividing something. If I have some number divided by a different number, and we're raising that to an entire, to a particular power, then you can distribute that, that power to both, the numbers inside the bracket. So that's the same thing as a to the power of m divided by b to the power of m. So they use the example, just getting that out of the way, they use the example 2 divided by y, and they're raising that to the power of 2. Well, that's the same thing as 2 to the power of 2 divided by y to the power of 2. So again, you can even, if you wanted to, you could take that a step further, and you can simplify that as 2 to the power of 2 would be 4 divided by y squared. You can't go any further than that. So that helps as we start kind of putting some of these together. And so that's what we're going to take a look at now, is what happens when we start putting some of these different rules together. Okay, so let me show you what I mean about how we can put these together. I want to start with a simpler one first. I'm trying to find one that would be a little bit easier on how we can put some together. And I want to show you with how those rules work and how we can only combine those that are considered like terms. So I'm going to grab one from the back, just doing a couple of them. So let's see, like if I had something like, I'm looking at page 24 and looking at some of the examples. I'm on number 13, and then it's letter C. It says this, so even if you don't have your book, I'm going to write it right here. So it says 5p to the third and q to the negative second. So we're putting a couple of these, not a couple of the rules, but in order for us to simplify, we have to think, this one actually only involves the negative exponent rule. Remember what happens when we see that negative exponent, we need to move that to a denominator, and that exponent is attached to this q right now. So this whole thing is going to need to move. Whereas 5p to the third, there is nothing wrong with that. So what it does is it's not that negative is wrong, but it doesn't move. So what happens is just the q squared simply just moves to a denominator because of that negative exponent rule. And that's actually as far as we can simplify it. Because p and q are different variables, they cannot be combined. Remember that rule, even if we were looking at these, if we were to apply the quotient rule even now, we couldn't. Since p and q are different letters, they are considered unlike terms. So this is as far as we're going to be able to simplify letter C there. Let's see, I'm trying to find, I tell you what, let me give you a little bit more of an elaborate one, and one that you guys can see we'll be able to, excuse me. No, this one won't be as elaborate. Let me show you what I mean. So let's put a couple of these rules together. Let me show you this. Let's say I have x to the negative sixth times x to the, let's say, 10th. And that's being divided by x to the third. So let's think about this for a second. There's a couple things we have going on here. All of these are the exact same variable with different exponents. So because they're all the letter x, that means they're all the same base. So some of these rules can be applied here. So let's start with the very top. Up at the very top there, we have x to the negative sixth times, since they're right next to each other, it represents multiplication, times x to the 10th. So that's our product rule. Our product rule says that when we're multiplying the same base, remember we can look at those two exponents, our negative 6 and our 10, and remember we can simply just add those two together to simplify that further. So when we do that, we're going to get x to the, what's 10 plus negative 6? That would be 4, positive 4. Okay, and then that's still over x to the third. So simplifying this a little bit further, now we can apply the quotient rule. Remember, the quotient rule says when we're dividing two numbers of the same base, then all we have to do is subtract their exponents. So there's 4 and 3. We're just going to take 4 minus 3. because that's the quotient rule, and that would give us x to the first, and anything to the power of 1 would just be itself. So that means this just simplifies down to x. All of this from the very beginning just simplified down to x. So that would be our answer. Okay, let me show you then, taking that a step further, I'm actually going back to page 21 and looking at an example on that page and what they provide for us. I'm looking at letter B on page 21 in that example 3. I won't give you anything like letter A. We're not going to deal with too many fractions in this class, so don't worry about that. But I'm looking at letter B, and we're going to be able to take a look at a couple different rules here. So letter B, we have 14 a squared times b to the 7th all over 2a to the 5th b, and then this entire thing is being raised to another power of -2. So we're going to be able to apply actually a couple different rules here. We definitely can see what's taking place inside the bracket. We're going to be able to look at the quotient rule because we're dividing the top by the bottom. We'll be able to look at that. We are going to end up seeing a negative exponent rule here being applied, and then we're also going to see a power rule, that when we have exponents being raised to a certain power, remember how you know, when a number is being raised to a power and then that's being raised to another power, how we apply that rule, how we end up just multiplying. So let's simplify this first. What I want to do is I'm going to simplify everything that's just inside this bracket first before we even think about that -2 there on the outside. Whoa, that is a horrible arrow. There we go. Okay, so starting with simplifying every like term. Remember, like terms meaning when they're the same number or same, you know, base. Looking here first at 14 and 2, since those are both numbers, I can actually go ahead and divide 14 divided by 2. And we know 14 divided by 2 is 7. So here's what we're going to start. And we're just simplifying what's inside the bracket first. So that's right there. 14 divided by 2 is 7. Now looking at the middle, I have my a's. I can combine those a's. So remember, when they're the same base, I've got my quotient rule, which says to take the exponents and subtract them. So 2 minus 5 is what we're going to look at here. I'm looking at just those two variables, these two right here. I'm not variables, I'm sorry, exponents. 2 minus 5 would give us -3. So that would then simplify to a to the -3rd. I know that's a negative exponent, and we will apply that here in just a second, but let's just simplify as far as we can right now. So that was the a's that we've simplified. Now we're going to simplify the b's. So same thing, we have the same variable, we just need to subtract their exponents. Now b in the bottom there doesn't have an exponent. When it doesn't, we always understand that to be 1. So even though there's nothing there, remember, it's not b to the 0 power, because anything to the 0 power would be 1. Like the whole thing would just simplify to 1. But if you don't see any exponent on a number, we assume it to be 1. So that would be the same thing as b to the 1. So in simplifying my b's there, I'm going to take 7 minus 1, which we know would be 6. So this would simplify to b to the 6th. So we've simplified those b's. So now we've simplified everything inside the bracket as far as we can right there. Remember, that entire thing is being raised to the negative, or to the power of -2. So now we need to take this a step further. Let's now apply our power rule, which says when we have something, you know, in parentheses and we're raising it again to another power, we need to do that. We need to actually apply that. So breaking this down a little bit further, if, you know, what we're thinking of is kind of the distributive property. I tell you what, let me get some of this confusing stuff out of the way here. And let's take what we have simplified right now. Right now I have 7a to the -3rd, b to the 6th, all raised to the power of -2. So let's think about it this way. What we're going to do is, it's almost like we're distributing that -2 to each part of what's inside the parentheses here. I'm going to apply that to the 7, to the a to the -3rd, and then to the b to the 6th. So if we want to break that down, the book shows us how we can break that down a step further here, that's like saying 7 to the -2. A is right now being raised to the power of -3, but we are going to then multiply that again by, so that's going to end up being multiplied by -2. Remember, that's what, oh, whoops. So remember, that's what happens when we have a power raised to another power. We end up just multiplying those two numbers. And then that's what we're going to do here with b, that we're going to take 6 and also multiply it by -2, because we're just distributing that -2. Okay, so what that means is we now have 7 has, is being raised to a negative exponent. So we're going to have to apply the negative exponent rule there. So, just simplifying that to show you what that's going to end up looking like is going to, yet again, be moved to the denominator. So that is going to be 7 to the power of 2, but on the bottom. Whereas when we multiply those two numbers, remember, negative times a negative, I'm looking at this right here, -3 times -2 is +6. So that part is just going to simplify to +6. So that's going to end up being on the top. Whereas then looking at these two, +6 times -2, we know a positive times a negative gives us a negative. So this is another, where we're going to have to move something to the denominator. So this is going to be 1 over b to the 12th. So simplifying this as far as we possibly can, when we combine all these together, what happens is my a to the 6 can actually stay on top. And, again, if we look at what's going on top here, so here is, let me circle this in yellow. Everything that's going to be able to remain on top is right here. 1, a to the 6th, and 1. Well, 1 times anything is just itself, so that means just we're going to leave a to the 6th on top, whereas everything down here will be on the bottom. So I'm going to write that in yellow up here on the top where I have some space. So that means a to the 6th will remain on top. Underneath is 7 squared, but if you want to go ahead and simplify that as far as you can, that 7 squared we know is 49, and then b to the 12th. I can't simplify that any further. So this is as far as we can go, since now we have all unlike terms. I can't combine a with b. 49 is a number, so it just remains where it is, and that's as far as we will simplify that. So you may get some like that as well, where you have to then just combine those and think about how if anything is ever outside of parentheses, you can distribute that, and how you can just simplify that as much as possible. But remember, you can only combine like terms. So when you have different letters, like in this case, then that's as far as you can go. So remember, that was the example on page 21, that was letter B, and then they even walk you through that very similarly in that page right there. Okay. So I know that's a lot, putting all that together. Let's see if there's any more samples for that. I tell you what, let me take a look at a very similar one that maybe is a little bit less complex. I'm looking at number 26 in the review section on page 25. And let me show you this one. So I know we haven't worked too much with fractions and simplifying of fractions. That last one was kind of easy because we had 14 over 2, and so we know that 14 divided by 2 was 7. So that was pretty easy to simplify. But on number 26 here, on page 25, this is what this looks like. This says 10a to the 3rd, b to the 11th, divided by 25a to the 7th, b to the 3rd. So this is very similar to what we just looked at without that being raised to another power. So that's going to be something we won't have to think about on this one. So we are going to simplify just like we did on the last one. We're going to simplify the numbers, the a's, and the b's, because again, they're all considered different terms. We can't combine unlike terms. So the problem here with 10 and 25, if I took 10 divided by 25, we're going to end up with a decimal. And we don't want that. We want to actually only be working with whole numbers. We don't want to turn that into a decimal. So I'm going to kind of give you a brief tutorial on reducing fractions if you're not already familiar with that. But we can look at this as the fraction 10 over 25. I'm looking at just this right now. And 10 over 25 can actually be simplified, or what's also known as reduced. If you're familiar with fractions, just hold tight for just a second. If you're not, here's how we reduce fractions. We reduce fractions by looking at both the top and the bottom number. and if both the top and the bottom can both be divided by the same thing. So right now, 10 and 25 are both multiples of something, but they both have to be a multiple of the same something. Like for instance, on the top there, 10, I can divide 10 by 2, just looking and thinking about that. So I'm looking at this fraction right now. So yes, 10 can be divided by 2. That would easily give me 5. That will totally work. But 25 divided by 2 would give me a decimal, and that is not what I want. I don't want to work with decimal. I can't reduce that to 5 over 12.5. That is not an appropriate reduced fraction. So we want to be able to think about what I can divide both of them by, where I get my answer as a whole number in both cases. And so you probably are thinking 5. Both 10 and 25 are actually multiples of 5. So therefore, that's what we're going to reduce them by. That's how we reduce fractions. We just divide them both by the same number. 10 divided by 5 gives me 2. 25 divided by 5 gives me 5. So 10 25ths can reduce to 2/5. I cannot reduce that any further because both 2 and 5 can't both be divided by the same thing. The only thing I can divide 2 by to make it smaller would be 2, and 5 divided by 2, very similarly, would give me just a decimal. And I don't want that. So this is as far as that is going to reduce, is to 2/5. So what that means here in our, in our in our problem that we're working with right now, that means that I can simplify just those numbers. So right now I'm looking at, again, like we did on the last one, simplifying 10 and 25. I'm going to simplify that to 2/5 because I look at it as a fraction when I have a case like that. Again, the last one was different because we could just take 14 divided by 2. That simplified, well, I don't know why I wrote 17. 14 and 2, well, if you think about it, both 14 and 2 can both be divided by 2. 14 divided by 2 is 7. 2 divided by 2 is 1. 7 over 1 is the same thing as 7. So that's why we just simplify that to that. Okay, let me get that out of the way. Oh, whoops. So this was 2/5. Okay. Now looking at the a's, so applying our exponent rule here. So a and a to the third divided by a to the seventh. Remember what that's going to look like. We have a quotient rule that needs to be applied here. So we're going to take 3 minus 7. So 3 minus 7 we know would give us -4. So since I'm going to write it off to the side, a to the -4, remember, would reduce to 1 over a to the +4 when we apply that negative exponent rule. Since in my answer down here I already have a fraction, I already have a top and a bottom, then we don't have to put that 1 on the top. I can just go ahead and put that a to the 4th down on the bottom. And then finally, when we're simplifying our b's, b to the 11th divided by b to the 3rd means just 11 minus 3, and we know 11 minus 3 would give us 8, and since it's +8, then that means it just remains on the top. So this b to the 8th would just go on top. So this simplifies to this. It would be 2b to the 8th over 5a to the 4th is as far as we can simplify that. And then we'd be finished on that one. So we're applying, again, in some of them, we're applying a couple different quotient rules. Sorry, I can't talk today. A couple different quotient rules. You can see a couple of them. You'll see ones like in that example page on page 25, like number 15. You'll see some maybe like number 18 where you have to apply that power rule. The product rule. We just did one like number 21 where it's all the same variable. So you had to apply the product rule and the quotient rule. And we just did, we just did number 26. So you may see one like number 26 or number 25. And then we did more of an elaborate one, which is more like number 44, where we have, kind of all kinds of different things going on inside parentheses, and then we raised it to another power. So those are some good practice problems for you if you're looking at that page. But go through that, and I'll also send you a review video on this to play around more with these different exponent rules. And I'll review before the quiz next week so that we, if we have any questions, we can go over that for sure. Okay, next thing I want to show to you guys is scientific notation. I think scientific notation is a little bit easier than what we just talked about with all these different rules for our exponents. So scientific notation starts on page 22. What scientific notation is, it's a different way of writing numbers that happen to be especially really long. Okay, so it's a different way of writing numbers that are maybe really long. What I mean by that is, like, for instance, if I had, say, I don't know, 6 million, that's a pretty long number. There's a different way that we can write that to make it a little bit, condensed. Same thing even when we have really small numbers. So even if I had this is a decimal here, 0.00007, something like that. These types of really long numbers. So what scientific notation does is it's just a different way of writing. It's just a different form of writing these numbers. And I'm going to explain this, and it's actually a whole lot easier than how this is going to sound. But scientific notation follows this form. It's going to be written as some number that falls between 1 and 10, but really it's actually between 1 and 9.9. You don't want it to be 10, and I'll explain why. But you're going to turn any number by moving the decimal point. You're going to get it to where it just falls between 1 and 10. And you're going to write this out as that number times 10 to the power of n, and that n represents the decimal movements. So let me show you what I mean. So decimal movements. Okay, so let's say this. Let's say we did have 6 million. So 6 million is a whole number. Because it is a whole number, we assume there's a decimal all the way down here on the very far right. What I want to do is I want to move that decimal as many times as I possibly can to turn this into a number that just falls between 1 and 10. So if I did that, if I moved it, say, 1, 2, 3 times, that would get me down to 6,000. Okay, you can see I've just shrinking this number down. If I move it 4, 5 times, I'm now to 60, but I need it to fall between 1 and 10. So moving it 6 times, moving that decimal to right here behind the 6 would make it 6. And that absolutely falls between 1 and 10. So I'm going to stop there at 6 movements. Had I have gone too many, if I accidentally moved that one more time, if I moved it 7 times, that would make it 0.6. And that's obviously not between 1 and 10. That's too small. So I want to go make sure that I get it to where it's just between 1 and 10. So writing this in scientific notation, I'm just going to write it as 6 times 10 to the power of, well, since I moved it 6 times to get there, to the power of 6. And so that's my number written in scientific notation, which makes sense if you think about it. 6, if you think about what 10 to the 6 means, 10 multiplied 6 times would be 1 million. If you actually did that, 10 times 10 times 10 times and 6 times is actually 1 million. And 6 times 1 million is 6 million. But it's just, again, this is understood as scientific notation. Okay, let's do another one. So remember that. This is going to follow this form. A times 10 to the power of n. And n represents the decimal movements. So let's say now I have, let's take something smaller. Let's say 32,000. Just 32,000. Another big number. So again, we assume this decimal is down here at the end. Moving that once would make that 3,200. Twice would make it 320. 3 times makes it 32. Again, I'm getting there. I'm shrinking it down. 4 times would make it 3.2. And even though it's a decimal, that decimal absolutely does fall between 1 and 10. And that's my idea. Remember, A must be between 1 and 10. So we write that as 3.2 times 10. And since I moved that 4 times, it's going to be to the power of 4. So there is this number written in scientific notation. You can do that really with any number. If I have even if I just had a small number like this, 450, we know that that number, has a decimal at the end here. Moving that as many times as I can just to make it fall between 1 and 10. Moving it once would make it 45. Twice would make it 4.5. And that falls between 1 and 10. Remember, moving it too many times would make it 0.45, and that's smaller than 1, and I don't want that. So this is what number I want that to be. And so I'm going to write that as 4.5 times 10 to the second, since I only moved that decimal 2 times to get there. So this would be how I write that in scientific notation. But I mentioned that even small numbers can be written this way. So if I had, say, 0.0008, and I want to write that in scientific notation, so here's my decimal in this number. So now my decimal needs to go the other direction. Right now it's very, very small. I have a number that's much smaller than 1, and I want to get it to where it falls between 1 and 10. So therefore I'm going to now have to move it to the right. The only thing that's going to change on these, we're still going to write it the exact same way, but now my exponent is simply just going to be negative instead. So what that means is when I move it once, that's 0.008, 2 would be 0.08, 3 is 0.8, still too small, 4 times would put that decimal right behind the 8, making it the whole number 8, and that's what falls between 1 and 10. So I'm going to write that in scientific notation as 8 times 10. I moved it 4 times, but I'm going to call that negative 4 since I moved it in the other direction. So anything that starts off as smaller than 1 is going to have a negative exponent. Okay, looking at another one. Let's say I have now 0.000053. Okay, so I need to move this decimal. Again, I'm moving it to the right this time, so I'm going to move it 1, 2, 3, 4, 5. Moving it 5 times would make that 5.3. I chose to move it 5 times again because if I only moved it 4 and put the decimal here, that would make it 0.53. That's too small. If I went too many times and moved the decimal here, that would make it 53, and that's bigger than 10, so that would be too big. So I stopped at the right number of places because I want it, again, to fall between only 1 and 10. So 5.3 is that number that does that, so I write that as 5.3 times 10, since I moved it 5 times, but since I moved it 5 times to the right, that's going to be to the negative 5th. Okay, and we write it this way because here's what this tells a person who's reading scientific notation. So if I had, let's say I'm gonna write down that first number that we started with, but in scientific notation, 6 times 10 to the 6. Remember that was 6 million. Here's what it tells a reader, anybody who has scientific notation number written in front of them. What this tells them is to start with this number, so our 6, and take the decimal that's in that number. So 6 is a whole number, so there's the decimal right there behind it, and move it this many times in that direction. So what I mean by that direction is because this is positive 6, I'm going to move it 6 places in the positive direction. And I mean, when I say positive direction, think about a number line. So on a number line, here's 0. Here are all my positive numbers going 1, 2, 3, 4, whereas all my negative numbers go this way, -1, -2, and so on. So therefore, so right is the positive direction and left is the negative direction. So that's what I'm going to do. I'm going to take that 6, and so take that decimal behind it, and that 6 times 10 to the positive 6 tells me to move that decimal 6 places in the positive direction. So 1, 2, 3, 4, 5, 6. I'd end up adding 6 zeros here, making this 6 million. Because now my decimal's down here. I don't have to write it since it's at the very end, but it's down there, so we understand that. That's 6 million. So any scientific notation number tells us if I wanted to turn it back into a standard form number, then that's what I would simply do. If I had, say, I don't know, let's say 4.8 times 10 to the third. So that means to take 4.8, so we know that there's a decimal right there between the 4 and the 8, so that's the decimal I'm working with, and it tells me to move it 3 places in the positive direction. So moving it once would make it 48, 2 times is going to make it 480, and 3 times would make it 4,800. Those 2 empty spaces right there just get filled with zeros. Remember, I've moved my decimal from here to now here, so therefore that gets moved, and my answer, you know, that decimal is assumed to be down there at the end. When it ends up at the end, we don't have to write it, so that just turns it into 4,800. Even when I have a negative exponent, that just means to move it in that direction. If I had 5.3 times 10, let's say to the negative third, then what that means is I'm going to start with that decimal between the 5 and the 3, so 5.3, And this exponent tells me to move it 3 places, but now in the negative direction. So that means I'm going to move it once, going to the left, would make it 0.53. Twice would make it 0.053. But 3 times, we're going to end up putting that 0 right there and fill those 2 empty spaces with zeros. And so that makes that 0.0053. So that's where my decimal ended up because I moved it 3 places in the negative direction. Okay, and just looking at one more of those. So if I had 7 times 10 to the negative 4th, then that means I'm going to start with 7. 7 has a decimal right there behind it. But my exponent tells me to move it 4 places in the negative direction, which again is to the left. So that would, moving it once puts it right in front of the 7, twice in front of an added 0, 3 times in front of another added 0, 4 times would put it in front of a third added 0 there. So that would be 0.0007. And then I always put, and you want to probably do the same, or not probably, you want to start doing the same. Any number that starts with a decimal, you want to also have a 0 in front of it. And that's the more proper way to write those numbers that start with a decimal, is putting that 0 in front of it. So that one there would be 0.0007. And that is scientific notation. So you'll see on the review video, you'll see a couple more with those. And then you'll see on next week's quiz, I'll do both of those. I will give you a standard form number, and I want to see how I wrote that. Yes, I gave you just regular numbers and said write the following numbers in scientific notation, so what we did at the beginning. And then the second part of the quiz, I gave you some scientific notation numbers and said to write the following numbers in standard form. So what we did just now there at the end. So you'll have both. Okay. Last thing I want to show you guys in this section, so we've skipped through we've gotten through scientific notation, so then that's the end of R.2. I want to go into, I skip over R.3 simply because we don't need to get into rational exponents and radicals. I'm going to skip over to R.4. So for those of you guys that are following along in your book, I'm going to tell you what page that's on as soon as I get there. Page 38. I want to show you guys just a couple things with polynomials, as that's going to help us lead into next class when we get into linear equations and simplifying those and solving for those. So what we're looking at here, we're looking at polynomials. We're not solving anything in these. We're also still just simplifying. But what I'm doing is I'm going to add polynomials. And what I mean by polynomial, it just means there's a lot of different parts of this expression. So you're going to see different exponents, and I'm going to show you what I mean by how we can combine different things in what's considered like terms. So we're going to start by adding polynomials and subtracting polynomials. So addition and subtraction with polynomials, a little bit different than multiplication, as when we talked about our different rules for exponents, remember that I want to show you this. Remember we had the product rule for exponents. When I have, say, b to the 5th, and I'm multiplying that by b to the 3rd, we can combine these two by adding those two together and making this b to the 8th. That's because, again, I showed you guys what that represented. B to the 5th is b multiplied 5 times, and b to the 3rd is b multiplied 3 times. So when I'm just multiplying these, it just becomes one long multiplication problem of 8 different b's, and that's why that can be simplified as b to the 8th. The problem when I'm adding these two together, oops, I meant to erase. Okay. The problem when I'm adding these two together is different. I cannot simplify, I cannot combine these two by adding them together because, again, remember b to the 5th and b to the 3rd, when I'm adding these, now it's not just one long multiplication problem like we saw a second ago. We've got this plus sign in the middle of it now. So when you're adding two of the same base that have different exponents, these are actually going to be considered unlike terms, and they cannot be combined. They'll only be able to be combined if they have the same exponent. So if I had, for instance, what I mean by that, if I have, say, how about 5, let's use b again, 5b to the 3rd plus b squared. And let's say that's a particular polynomial, and I'm adding that to 4b to the third plus 6b squared. So these are what's considered polynomials. I can combine this b to the third and this b to the third. So I can add together, since I'm adding these two polynomials, I'm going to add 5 plus 4, and that's going to become 9b to the third. I can only put those two together, and then I can put together the ones that are squared. So b squared in this first one, I know there's no number in front of it, so we assume that to be 1. So that's like 1b squared plus 6b squared would be 7b squared. So that's as far as I can go when adding polynomials. So I wanted to show you that to show you that there's a difference between when we're multiplying these exponents versus when we are adding these. So that's what we're going to look at first, is the addition of polynomials. So I'm going to actually show you guys the first example on page 39. I'm looking at letter A. If you don't have that, I'm going to write that up here on the board for you here. So I have negative 4w to the third minus 5w squared plus 6w plus 3. Sorry, I'm running out of room here. Plus, and I'll write the other one just right underneath it. Maybe that'll make it easier to see how we can combine these. So plus 8w squared minus 4w plus 2. So I want to add these two polynomials together. So remember, we can only combine like terms. And what you want to start with, it's, as you can see, you notice that each individual polynomial, so the first one here, this is the first polynomial that I'll put in blue parentheses. And then this is the second polynomial in red parentheses. It's called a polynomial, again, because there's lots of different components to this problem here. And I can only combine the like terms, but you notice how they're in order based on descending exponents. So you notice that the exponent on the first polynomial, the blue one, notice that it's w to the third first, then w squared, then w by itself, which is the same thing as w to the first, and then 3. So it's always going to be in that order. So that's a more common way to write polynomials, is to put the bigger exponent first. And so that'll help us too next week as well. So since there is, in the second polynomial, there isn't one that's to the third, it's going to actually be by itself. So it doesn't have anything to add to, so I'm just going to write that on its own. Negative 4w to the third. So in simplifying that, we're done with that. Now I have these two to combine, and I'll circle these in yellow. My w square, I have a minus 5, so we're going to look at that as negative 5, and then 8w on the second polynomial. So these two are being added together. So that means we're taking, think about it as negative 5, so it's still going to be w squared, but looking at just the numbers, I have negative 5 plus 8, and it's plus because of the operation that's between the two polynomials. Negative 5 plus 8 we know is positive 3, right? So that means I'm going to, in writing this in where we're simplifying, that's actually going to be written as plus 3w to the second. So we're finished with those. Now looking at my w's on their own, so meaning the w to the 1 is what I'm looking at next, and I'll just circle those in red. I have plus 6w, and down here that's minus 4w. So again, because my operation is plus, we're going to look at that as 6 plus negative 4 when we're simplifying that. So 6 plus negative 4 I know is positive 2. So because of that, and simplifying that one, that's going to be plus 2 to the w, or to w, not to the anything. It doesn't, it's raised to the power of 1. So that would just be 2w. And then lastly, I have our numbers to combine. So we have positive 3 and positive 2, and we're adding those two together, and we know 3 plus 2 is 5. So that last part would just be plus 5. The rest of these are all considered unlike terms, so I cannot combine these any further. So there is my completed answer. And they've worked that out for us. You can see that in the solution on page 39 as well. So remember, you can only combine your like terms. And guys, I'm not going to give you anything like letter B there. So I know they show a subtraction of polynomials. With the subtraction of polynomials, I'm not going to give you any decimals. I will always give you whole numbers, so you don't need to worry about that. But if, say, just for fun, if let's say I had the same exact polynomial that we just looked at, so this is just kind of a what if scenario. If I have, and I'm just going to write the exact same one, let's see, that was negative 4w to the third minus 5w squared, oh, that's a w, plus 6w plus 3. And let's say now we are subtracting the second w, so second polynomial. I cannot talk today. 8w squared minus 4w plus 2. Okay, so let's see what would that, the only difference between, the addition and subtraction of polynomials is we're just subtracting. When we have those like terms, we're subtracting the like terms. So once again, since 4w to the third, or negative 4w to the third, there isn't another w to the third to combine that with. So I'm going to just leave that down here on its own. Doesn't have anything to, I don't have anything to subtract from it, so I'm going to leave that alone. Now my w squared, I'm going to have, again, negative 5w and 8w. So 8w squared, I'm sorry. So we're looking at the negative 5 and the 8, but again, remember it's being subtracted. So now that's like saying negative 5 minus positive 8. So let's think about those integer rules. Negative 5 minus 8, remember the add a line, change the sign, is the same thing as plus negative 8. So therefore that would be negative 13. So in writing that, that would just be written out as minus 13 w squared. Now looking at combining the w to the 1, so it would be my positive 6w, and negative, since that's a minus sign, that would be negative 4w. So again, since we're subtracting these two polynomials, this would be positive 6 minus negative 4. Again, thinking of our integer rules, that would be the same thing as plus positive 4. When we add a line, change the sign. So 6 plus 4 would be 10. So that means this, and since it's positive 10, I'm going to write that as plus 10w when we combine those two. And then lastly, I have positive 3 and positive 2, but we are subtracting those. And positive 3 minus positive 2, we know is positive 1. So there is our simplified polynomial when we subtracted that. So that's the addition and subtraction of polynomials. So you'll see a couple examples with that in the review video. But remember, the big thing with that is that don't forget you can only combine your like terms. And the only thing I want to show you in the multiplying of polynomials, a little bit different than what they have in on page 39. We're not going to look at it that way. And again, I'm not going to give you guys anything with fractions in it, so you wouldn't see that example. You would see one like the second example. So let me actually give you one that's close to what you would see. Okay, I tell you what, let me do this. And it's just going to go back to that distributive property. And there's a reason why I really only cover that, because that's going to help us in doing some stuff we're going to look at next week too. So I am going to show you all a multiplication of polynomials. Sorry, I'm trying to find a good example. Okay, here's a good example. I am looking at page 44, and I'm looking at number 25. So looking at the review section, number 25 towards the bottom of page 44 shows you this. It shows 7m squared, and we are multiplying that by 2m to the fourth minus 3m plus 4. Okay, so with multiplication of polynomials, because our exponents are being multiplied, we can combine them when they're different exponents. Because remember my power rule, or my product rule, that says when I'm multiplying, say m squared times m to the fourth, which is what we're getting ready to do, remember when they're being multiplied, because they're the same base, I can just add their two exponents together, and these can be combined to just m to the sixth. So we will be able to do that when we are multiplying polynomials. Thinking back to what I showed you at the very beginning, those can be combined. So right here, what we're going to do is we're going to look at this and look at the this in terms of the distributive property. Remember we showed you that, we did that on today's quiz. That what I'm doing when this says 7m squared times everything in the parentheses, I can individually distribute that to each part of what's inside the parentheses here. And that's exactly what I'm going to do. So let's start with just that first one. So 7m squared multiplied by 2m to the fourth is what we're looking at right now. So we can go ahead and multiply the two numbers together, 7 times 2, which we know is 14. And then think of your product rule for our multiplication of those two exponents. I just showed you that one. M to the power of 2 multiplied by m to the power of 4. We can just add those two numbers together, and that would be m to the power of 6. Okay, so that's how we multiply those two exponents. So let's then look at these. So now I'm going to multiply 7m squared times negative 3m is the way that we want to look at that. Because again, it helps to see that minus sign as a negative to help us see how we're going to write that out. So look at that minus 3 as negative 3. So we multiply the 7 times negative 3, looking at just the numbers. That would be, since it's a positive times a negative, would be negative 21. And then our product rule, when we're multiplying m to the second, and I'm multiplying by m by itself, remember we understand that m by itself to be the m to the power of 1. So when we add those two exponents, that would make that m to the power of 3. Okay, and then the last one there, distributing that to the just number 4, then we can multiply the two numbers together. 7 times 4, I know is positive 28. Oh, let me change my marker here. Would be positive or plus 28. But don't forget that 7 has the m squared on it, so we can't leave that out. Even though the 4 didn't have that, since it doesn't have anything at all, it doesn't get combined or added, but we can't leave it out. It's part of that 7, so it has to be now part of that 28. So that's how we would distribute that. And that's what that would look like. So that's how you would multiply polynomials. And so that's exactly like the ones I would give you on the quiz. You have two, I'm looking at the quiz right now, and you have two on the quiz that are just like that you just simply need to distribute. There will only be one outside of the parentheses. So a little bit different than what you're seeing in some of those other examples. For those of you guys who have your book, and if you're looking at, say, number 29 or 30, I won't give you anything like that. Although you could do those, you're only going to see ones like what we have on the board here, where we have to just distribute. And so giving you another one, let's say we have this. Oops, hold on, sorry, having some issues here. Okay, there we go. Okay, so let's say we have this. Let's make it 5x to the third, and let's multiply that by, let's say, 2x to the fourth plus, let's say, 4x squared minus 5x minus 7. Okay, so this is a much longer one, but the same idea is put in place here, that we're just going to distribute that 5x to the third to each part of inside here, and then after that, they can't be combined any further because we'll only have addition and subtraction, and remember, they can't be combined because they will be unlike terms. But we can combine them when they're being multiplied. So 5x to the third, multiplying here first, we can multiply 5 times 2, we know is 10, so looking at just the numbers there. But then x to the third times x to the fourth would be x to the seventh. That's our, again, putting that product rule in place. And then moving on to multiplying by 4x squared. 5 times 4, since it's a positive 4, I know it's 20, so this is going to be plus 20. And then x to the third is what we're looking at right now, multiplying by its x squared, so looking at its exponent, we know that that would be x to the fifth. Okay, now distributing that negative to the negative 5x is how we will look at that. So we look at that as 5 times negative 5, which we know is negative 25. And then x to the third times just x to the 1 would be x to the fourth, is how we would look at that. And then distributing there down to the end, we look at that as 5 times negative 7, which is going to be negative 35. But again, since 7 doesn't have any variable on it, we just use the variable that's on the 5 that we just distributed, so we can't leave that x to the third out. So that's how that would be simplified. So although it's incredibly long here, again, now that it's x to the 7th and x to the 5th and x to the 4th and x to the 3rd, since they're just being added, subtracted, and subtracted here, I cannot combine that any further because those are considered unlike terms. So that's as far as we will simplify. Alright guys, so that is actually all I have for you today. So kind of short lecture on that. But if you guys have any questions, please, please, please don't hesitate to email me. Your homework for tonight is to complete the second ALEX assignment. If you have any questions about the ALEX, again, please, please, please don't hesitate to ask me any questions that you guys have. But again, we will review everything that we just talked about in this video. I will review it all before the quiz next week. All right, guys, see you then.